On the afternoon of May 2nd, the skies over west central Texas turned a color that anyone who has lived on the southern plains knows to fear. A deep, sickly green settled over the horizon. The air went still. And then, from the base of a rotating supercell thunderstorm that had been building for hours, a funnel reached down toward the earth and touched it with catastrophic force. What followed was one of the most violent tornado events to strike this part of Texas in recent memory. Multiple twisters carved paths across the landscape, but one storm stood apart from all the others. One tornado became something else entirely, something that meteorologists, storm chasers, and emergency responders would spend days trying to fully account for. A tornado that did not just damage what it touched, it erased it. This is the story of the May 2nd severe weather outbreak in west central Texas and the extraordinary violence of the tornado that struck the small town of Hawley. To understand what happened that day, you have to understand the atmosphere that was being built across the region in the days leading up to it. Spring in west central Texas is a season that plays by its own rules. The state sits at the collision point of competing air masses that have no equivalent anywhere else on the planet. Warm, moisture-laden air flows north from the Gulf of Mexico, pushing across the flat coastal plains and spreading deep into the interior. Meanwhile, dry air tumbles off the Rockies to the west, sliding eastward at altitude. And from the north, cold continental air can plunge southward with little geographic resistance to slow it down. When these three forces align in the right configuration, they create what atmospheric scientists call the ingredients for severe convective weather. And in the days before May 2nd, those ingredients were coming together with unusual precision. The Storm Prediction Center, the federal agency responsible for monitoring severe weather potential across the continental United States, had been watching the setup carefully. Their outlooks for the region showed increasing confidence that conditions on May 2nd would support not just thunderstorms, but supercell thunderstorms, the kind that rotate, the kind that produce tornadoes. By the morning of May 2nd, a dry line had set up across West Texas. A dry line is essentially a boundary in the atmosphere where the moisture content drops sharply over a very short horizontal distance. It acts like a trigger. As the afternoon sun heats the ground, air masses begin to lift along that boundary, and when the lifting is strong enough, thunderstorms fire along it explosively. Storm chasers and meteorologists across the region were already in position. The day had the look of something significant. The first storms initiated in the early afternoon, erupting along the dry line with remarkable speed. Within an hour of initiation, several of them had organized into supercells. Supercells are not ordinary thunderstorms. They are rotating storms driven by a feature called a mesocyclone, a column of rising, spinning air that forms within the updraft. They can persist for hours, traveling hundreds of miles, and they are responsible for the vast majority of the most violent tornadoes ever recorded. On the radar displays being monitored at the National Weather Service office and by meteorologists across the country, watching the live data feeds, the storms lit up. Hook echoes appeared on radar, the telltale curved signature that indicates a rotating updraft, capable of producing a tornado. The National Weather Service issued tornado warnings in rapid succession as the storms marched across the landscape. Multiple tornadoes touched down during the afternoon hours, carving paths across open ranch land, farm country, and the scattered small communities that dot this part of Texas. For most of the outbreak, the damage, while destructive, was consistent with what meteorologists categorize as the lower to mid-range of the enhanced Fujita scale. The system used to rate tornado intensity based on the damage left behind. Trees stripped bare, outbuildings demolished, fences swept away, vehicles tossed and tumbled. Significant damage, frightening damage, but the kind that belongs within the expected parameters of severe weather events in this part of the world. And then the Hawley tornado happened. Hawley, Texas is a small community in Jones County, sitting roughly 10 miles north of Abilene. It is the kind of place where people know their neighbors, where the landscape is open and the sky feels enormous, where life moves at the pace of the land. A community with deep roots in West Texas ranching and agricultural culture. A community that was about to have a May afternoon that no one living there will ever forget. The supercell that produced the Hawley tornado was already a formidable storm before it reached town. Storm chasers who were tracking it reported a well-organized mesocyclone and a clearly defined rotation visible on radar. The storm's structure, visible in video captured by chasers in the field, showed the hallmarks of a particularly dangerous supercell. A defined wall cloud, the low-hanging rotating cloud base that often precedes tornadoes, had been observed descending from the storm. The atmosphere was primed. The storm was ready. When the tornado touched down, it was already large, not a thin, rope-like funnel that sometimes characterizes the weaker end of the spectrum. This was a broad, powerful wedge, the type of tornado that sweeps wide swaths of destruction across everything in its path. Witnesses described the sound as overwhelming, that famous freight train roar amplified to an almost incomprehensible degree. The kind of sound that seems to come from everywhere at once, from the ground, from the sky, from inside your own chest. The tornado moved through the area with the full weight of a high-end violent storm behind it. And in the aftermath, when surveyors from the National Weather Service arrived to document what it had left behind, the damage told a story that placed this tornado at the upper end of the enhanced Fujita scale's third tier, an EF3, a rating that corresponds to wind speeds estimated between roughly 136 and 165 miles per hour. These are not gusts, these are sustained winds within the core of the vortex, winds powerful enough to destroy well-constructed homes, to strip bark from trees, to lift vehicles and throw them like crumpled paper. EF3 tornadoes represent a category of storm where survival in a poorly protected structure becomes genuinely uncertain. They are the tornadoes that fill the archives of the Storm Prediction Center with images of foundations swept clean, neighborhoods reduced to debris fields, landmarks that stood for generations simply gone. And the Hawley tornado was not just an EF3. Surveyors noted that it was a high-end EF3, meaning the damage indicators pushed toward the upper boundary of that rating category, closer to the threshold that separates EF3 from the catastrophic EF4 tier. The single most dramatic piece of evidence for the tornado's violence was what it left behind at one specific location in its path. A home, a structure that had been built on a concrete slab foundation, the standard construction method for homes in this region, where concrete is poured directly onto prepared ground to form the base upon which walls are framed, utilities run, and a family's life is built. When the tornado passed over this home, it did not leave damaged walls or a collapsed roof, or the kind of wreckage that still resembles, in however distorted a form, what the structure once was. It did not partially destroy the home, it took it, completely. Every wall, every piece of framing, every piece of roofing material, every item of furniture, every possession inside, it swept the entire structure away with such force that the concrete slab left behind was not covered in debris. It was clean. A swept clean slab is one of the most chilling images in all of tornado meteorology. It is the thing that appears in the training materials for National Weather Service damage survey teams. It is the benchmark by which extreme tornado violence is measured and communicated. When a tornado has enough power to remove not just a structure, but the evidence of a structure, to leave nothing behind but the bare foundation, you are looking at the work of a tornado operating at the violent end of the scale. Damage survey teams who walk these scenes describe the experience as deeply unsettling in a way that photographs don't fully capture. You stand on the slab. You can see the anchor bolts where the wall plates were once secured. You can see the drain lines in the concrete, and there is nothing else. The storm took everything else and carried it away. Some of it was found nearby, some of it scattered for miles. The tornado's path through the Hawley area was scrutinized intensely in the days that followed. Survey teams walked the damage swath, taking photographs, recording GPS coordinates, assessing each structure along the path and assigning damage indicators according to the standardized methodology developed for rating tornadoes on the enhanced Fujita scale. The system works backward from the damage, because we cannot directly measure the wind speed inside a tornado, except in rare cases where mobile radar or instrument packages happen to be in precisely the right location. We infer the wind speed from what the wind did to the things it encountered. A well-constructed wood frame home, properly anchored to its foundation, can withstand certain wind speeds. When a tornado removes that home completely, we have a quantifiable data point for what minimum wind speed was present. Reinforced masonry walls fail at certain speeds. Large hardwood trees, their root systems intact, defoliate at lower speeds, debark at higher ones, snap at higher still, and uproot at the strongest. Every tree, every power pole, every vehicle, every building in the damage path becomes a measurement instrument, and the survey team reads them all. What the survey teams read in the aftermath of the Hawley tornado told the story of a vortex operating with the kind of energy that makes this region's severe weather history. High-end EF3 damage across a significant swath of the landscape, with the swept-clean slab standing as the most unambiguous evidence of the tornado's peak intensity. Miraculously, the death toll from the Hawley tornado was not what a storm of this intensity might have claimed. The National Weather Service warnings had been issued with sufficient lead time that many residents had sought shelter. In tornado-prone parts of Texas, shelter awareness is not a casual thing. It is part of how people live. Generations of families in this region have grown up understanding that when the sky looks a certain way and the sirens sound, you get low and you get to the sturdiest interior room or structure available. That cultural knowledge saves lives. But the warning system that protected people on May 2nd did not emerge from nothing. It is the product of decades of hard work by meteorologists, atmospheric scientists and engineers who have devoted their careers to understanding severe convective storms and improving the accuracy and lead time of tornado warnings. The story of how that system was built is inseparable from the story of storms like the one that struck Hawley. The science of tornado detection advanced enormously in the latter half of the 20th century. Before the deployment of modern Doppler radar networks across the United States, tornado warnings were issued primarily based on visual reports from spotters and law enforcement on the ground. A tornado had to be seen before a warning could be issued. That meant lead time was minimal. By the time a warning reached the public through whatever communication channels were available, the tornado might already be overhead. Doppler radar changed everything. By measuring not just the location and intensity of precipitation, but the velocity of the precipitation, essentially detecting the motion of rain and hail particles within a storm, Doppler radar allowed meteorologists to see rotation inside a thunderstorm's updraft before a tornado ever touched the ground. They could see the mesocyclone developing. They could identify the velocity couplet, the signature on radar of adjacent areas within a storm where winds are moving in opposite directions, indicating rotation. That signature means a tornado is possible or probable even before one has formed, and it gives forecasters the ability to warn ahead of the event rather than after. The national network of operational weather radar was substantially upgraded through the 1980s and 90s, culminating in a nationwide system of high-powered Doppler radar sites that collectively provide coverage across the continental United States. Each site scans the atmosphere continuously, sending out pulses of microwave energy and listening for the return. The data streams into the National Weather Service forecast offices in near real time, where meteorologists watch it unfold on their displays and make warning decisions that go out over wireless emergency alerts, weather radio, television, and digital platforms to the public. On May 2nd, those systems were working exactly as designed. The National Weather Service office, responsible for the Abilene area, which includes Jones County and the Hawley community, was tracking the storms as they developed, issuing tornado warnings with lead times that gave residents the chance to take protective action. The infrastructure of modern weather science was operating in the background of what happened that day, invisible to most people, but absolutely present. Storm chasers were also in the field, as they are on nearly every significant severe weather day in the southern plains. The community of storm chasers in the United States spans everyone from professional meteorologists conducting research to trained volunteers who provide ground truth reports to the National Weather Service to independent videographers documenting storms for public awareness and education. On a day like May 2nd, dozens of chasers converge on the most promising areas, tracking storms, capturing video, and relaying information back to forecast offices and to the public through social media and live streams. The video captured by chasers on May 2nd documented the Hawley tornado and the other storms of the outbreak in extraordinary detail. Footage circulated widely in the days following the event, showing the breadth of the vortex, the debris cloud rising around its base as it moved across the landscape, the transformation of the sky overhead as the supercell structure rotated and evolved. For the public watching from safe distances, the footage provided a visceral sense of the power involved. For meteorologists and researchers, it provided additional data points to complement the radar and damage survey records. The study of tornadoes, particularly the most violent ones, is an ongoing scientific endeavor. Researchers affiliated with universities, federal agencies, and private organizations are continually working to refine the understanding of how tornadoes form. why some supercells produce tornadoes and others do not, what determines whether a tornado will be weak or violent, and how to better predict those outcomes. These questions are not merely academic. Every incremental improvement in understanding translates eventually into incremental improvements in warning capability, which translates into lives saved. One of the persistent challenges in tornado research is the difficulty of making direct measurements inside the most intense vortices. The environments that produce violent tornadoes are, by definition, extremely dangerous and destructive. Getting instrumentation into the core of an EF3 or EF4 tornado is extraordinarily difficult. Research programs have attempted it using armored instrument packages deployed in the path of oncoming tornadoes, using mobile radar units that can probe tornado interiors from relatively close distances, and using unmanned aerial systems in the storm environment. Each approach has yielded valuable data. None of them has fully solved the problem of characterizing the internal wind field of the most violent tornadoes. The enhanced Fujita scale itself, the rating system applied to the Hawley tornado, was introduced in 2007 as a refinement of the original Fujita scale, developed by the University of Chicago meteorologist Ted Fujita in the 1970s. Fujita, who became known as Mr. Tornado for his pioneering work in severe weather research, developed the original scale based on the relationship between damage and estimated wind speed. The enhanced Fujita scale updated those wind speed estimates using modern engineering data and expanded the list of damage indicators to include a wider range of structure types and vegetation. The rating process for tornadoes is always a post-event activity. It requires trained survey teams to walk the damage path, document what they find, and apply the standardized criteria. The ratings assigned are consensus products, representing the best scientific judgment of the meteorologists and engineers who conduct the survey. In cases where the damage evidence is particularly compelling, as it was with the Hawley tornado's swept clean slab, the rating process has clear and unambiguous anchors. In other cases, where the damage is more ambiguous, or where the tornado crossed open land without encountering many structures, the rating carries more uncertainty. The Hawley tornado's EF3 rating, and specifically its characterization as a high-end EF3, reflects the weight of evidence left behind in its damage swath. The swept clean foundation was not the only indicator. The pattern of destruction along the tornado's path told a coherent story of winds that exceeded anything that falls into the lower or middle portions of the scale. Trees were not just blown over, they were shredded. Vehicles were not just pushed off roads, they were displaced significant distances and twisted beyond recognition. The debris field extended far beyond the immediate swathe of the tornado's visible path. Debris lofting is one of the more remarkable and scientifically interesting phenomena associated with violent tornadoes. When a tornado reaches sufficient intensity, it can carry debris not just horizontally but vertically, lofting material into the upper portions of the storm. Pieces of insulation, fragments of roofing, sections of framing lumber, even heavier objects have been found miles from where a tornado crossed. In the most violent tornadoes, debris has been carried dozens of miles from its origin point. The dispersal of debris from the Hawley tornado was consistent with the violence indicated by the damage survey. For the residents of Hawley and the surrounding communities, the days following May 2nd were consumed by the immediate human realities of a major tornado strike. Search and rescue, damage assessment, the accounting of injuries, the work of neighbours helping neighbours that characterises the aftermath of disasters in small communities across the American interior. Organisations including the American Red Cross, local emergency management agencies, and volunteers from surrounding towns converged on the affected areas to assist with shelter, food, and the beginning of the long process of recovery. The recovery from a tornado at this scale of violence is not a short process. The physical reconstruction of damaged and destroyed structures takes months, sometimes years. The insurance process, the permitting process, the sourcing of materials and contractors in a region where the construction industry may already be strained, all of it unfolds slowly. And the psychological recovery, the processing of what it means to have your home or community struck by a violent natural phenomenon, carries its own timeline that does not map neatly onto the progress of physical reconstruction. What happened in Hawley on May 2nd fits into a broader pattern in the climatology of this region. West central Texas and the surrounding southern plains have produced some of the most significant tornado events in American history. The reasons are geographic and atmospheric. The collision of air masses, the lack of terrain that would disrupt developing supercells, the abundant solar heating of the flat land surface that energizes convective storms. All of these factors combine to make this one of the most tornado-prone regions on Earth. The corridor stretching from West Texas northward through Oklahoma, Kansas, Nebraska, and into the Dakotas is commonly referred to as Tornado Alley, though meteorologists note that violent tornado activity is not confined to this corridor, and that the boundaries of the high-risk zone have appeared to shift in recent decades. The question of whether tornado activity is changing over time, in frequency, in intensity, in geographic distribution, is one that atmospheric scientists are actively investigating. The observational record is complicated by the fact that modern detection capabilities are far superior to those of earlier decades, meaning that apparent trends in tornado frequency are difficult to disentangle from improvements in the ability to detect and document events. The most violent tornadoes, the EF3 through EF5 events, leave damage signatures that are harder to miss even with older detection methods, making the long-term record for the extreme end of the scale somewhat more reliable than the record for weaker events. What the science does suggest is that the atmospheric ingredients that support severe thunderstorm and tornado development are sensitive to changes in the broader climate system. The moisture content of the lower atmosphere, the temperature contrast between air masses, the behavior of the jet stream that steers weather systems across the continent, all of these factors interact with climate variability in ways that researchers are working to characterize. It is a question with real stakes for communities like Hawley, for the emergency managers and infrastructure planners responsible for their safety, and for the meteorologists and scientists dedicated to understanding and predicting what the atmosphere will do. The National Weather Service continues to refine its warning operations following every significant severe weather event. Post-event analysis of warnings, radar data, storm reports, and damage surveys feeds into the operational learning process that incrementally improves performance over time. The lead time available before the Hawley tornado struck, the accuracy of the warning's geographic scope, the effectiveness of communication to the public in the affected area, all of these dimensions are examined in the aftermath of events like May 2nd and used to identify areas for improvement. Technology continues to evolve in ways that hold promise for further improving severe weather prediction and warning. Dual polarization radar, now standard across the national radar network, provides meteorologists with additional information about the size, shape, and type of precipitation within storms, improving the ability to detect tornado debris signatures, which appear on radar when a tornado's lofting material, confirming that a tornado is actually on the ground. Advances in numerical weather prediction modeling are improving the accuracy of short-range forecasts of storm initiation and evolution, and research into the use of machine learning techniques applied to large meteorological datasets is beginning to yield tools that may eventually support more accurate prediction of which supercells will produce tornadoes and which will not. The tornado that struck Hawley, Texas on May 2nd was a high-end EF3. Wind speeds that shred structures, sweep concrete foundations clean, and carry the pieces of ordinary life miles from where they stood. But it was also, in the longer view, a chapter in the ongoing story of human beings reckoning with the atmosphere of this planet, learning to understand it, learning to predict it, building systems and communities capable of surviving it. The residents of Hawley know their landscape, they know the spring sky and what it can bring, and in the aftermath of May 2nd, in the work of clearing debris and rebuilding and checking on neighbours, they demonstrated what generations before them demonstrated every time the storms came through. That the human response to catastrophe on the southern plains is not simply survival, it is continuation. The storms come, the people remain, and the work of understanding the sky continues. The work of understanding the sky is not new. It predates meteorology as a formal discipline by centuries, predates the invention of the weather balloon and the radar dish and the satellite, predates every tool that modern atmospheric science deploys. Human beings who lived on the southern plains and in every other region where the atmosphere puts on violent displays, learned to read the sky because their survival depended on it. They learned it the way all survival knowledge is learned, through close observation, through painful experience, and through the transmission of what was observed and experienced to the next generation. The Comanche and Kiowa peoples who lived across this part of Texas for generations before European settlement understood the spring sky in ways that were deeply practical. They knew when to move, when to seek shelter in the breaks and arroyos that cut across the flat uplands, when the colour of the horizon signalled something more serious than an afternoon thunderstorm. That knowledge was not written down in any systematic way. It lived in the people, and it was accurate. It had to be accurate. The consequences of misreading the sky were immediate and severe. The Spanish colonial period brought different ways of moving through and interpreting this landscape, but the basic challenge remained constant. The atmosphere of West Texas does not negotiate. It presents conditions, and the people living beneath it adapt or suffer the results. What changed across the centuries was not the atmosphere, but the tools and systems that human beings developed to monitor, predict, and respond to it. The earliest formal weather observation networks in the United States were scattered and inconsistent. The Weather Bureau, the predecessor to the National Weather Service, was established in 1870 under the authority of the Army Signal Corps, tasked with collecting meteorological data and providing storm warnings for Great Lakes navigation. Its responsibilities expanded over the following decades to include the interior of the continent and the challenge of severe weather prediction, but the tools available were primitive by modern standards. Surface weather observations taken at fixed stations, transmitted by telegraph, plotted on paper maps. Forecasters worked from synoptic charts, drawing isobars and fronts by hand, making predictions that were often right about the large-scale pattern and frequently wrong about the specific timing, location, and intensity of severe convective events. The fundamental problem was that tornadoes form at the mesoscale, a size range that falls between the large-scale weather patterns visible on synoptic charts and the small-scale turbulence that characterizes ordinary atmospheric flow. A supercell thunderstorm occupies a footprint of perhaps 20 to 50 miles. The tornado it produces occupies a footprint of perhaps a few hundred yards to a mile or two. Both are essentially invisible to a network of surface weather stations spaced 30 or 50 or 100 miles apart. You could see the conditions favourable for tornado development. You could not see the tornado until someone on the ground reported it. For much of the first half of the 20th century, the National Weather Bureau had an informal policy of avoiding the word tornado in its public forecasts. The reasoning was partly paternalistic, a concern that the word itself would cause panic. That policy was revised in the 1950s, and the revision was driven in part by a series of catastrophic tornado events that demonstrated beyond any reasonable argument that withholding information from the public about tornado threats was not protective, it was deadly. The tri-state tornado of 1925 remains the deadliest single tornado in American recorded history. It travelled nearly 220 miles across Missouri, Illinois, and Indiana, staying on the ground for hours, killing almost 700 people. There were no tornado warnings issued. People in its path had no meaningful advance notice. The storm swept through towns and rural areas alike, and those who survived were the ones who happened to be in structures sturdy enough to provide some protection, or who saw the storm coming with enough time to run. Joplin, Missouri in 2011. The city was struck by an EF5 tornado on May 22nd. 161 people died. This was not a case of no warning. A tornado warning had been issued roughly 20 minutes before the tornado struck. But the circumstances of that warning and its receipt by the population in the path of the storm illustrated a set of challenges that go beyond the technical capability of the detection and warning system and into the human dimensions of risk communication. Many people in Joplin heard the warning sirens. A significant portion of them did not immediately seek shelter because, as researchers who interviewed survivors discovered, the sound of tornado sirens had become normalized in a way that dulled the sense of urgency. Sirens sound regularly during severe weather across the southern plains. Most of those soundings are not followed by a tornado strike, or not by a strike at the location of the person who heard the siren. Over time, for some people, the siren becomes background information rather than a command to act immediately. Researchers call this warning fatigue, and it is one of the more vexing problems in the science of risk communication, because the solution is not obvious. More sirens, louder sirens, more frequent sirens do not help. In some cases, they make the problem worse. The challenge of communicating tornado risk in a way that moves people to take appropriate protective action is a research area that sits at the boundary of atmospheric science, psychology, and communication studies. The meteorological community has invested significant effort in understanding how people receive, process, and respond to weather warnings, and what the research has found is that the message content matters as much as the message delivery. People respond more strongly to specific localized information than to broad regional warnings. A warning that says a tornado has been confirmed and is moving northeast at 45 miles per hour toward a specific name location moves people to action more reliably than a warning that says conditions are favorable for tornado development across a large area. The specificity creates a cognitive connection between the abstract threat and the person's specific situation. The National Weather Service has worked to incorporate this research into how warnings are written and communicated, shifting toward more geographically specific language and more explicit statements of the threat. Wireless emergency alerts, the system that pushes tornado warnings directly to cell phones within the warned polygon, represent a significant advance in the reach of the warning system. Before wireless emergency alerts became widespread, your ability to receive a tornado warning depended on whether you happened to be watching television, listening to weather radio, or were near a siren. Wireless emergency alerts reach nearly every person with a cell phone in the warned area, including visitors who don't know the local warning infrastructure, people who are asleep, people who are indoors away from windows and can't see the sky. The shrill tone of a wireless emergency alert landing on a phone in the middle of the night has probably saved a meaningful number of lives in the years since the system was deployed. The integration of multiple communication channels is deliberate. Weather radio broadcasts continuously and does not require active monitoring. Television stations interrupt regular programming and deploy local meteorologists who provide context and guidance. Social media platforms have become important dissemination channels for warning information, for better and sometimes for worse, since the same platforms that can spread accurate official warnings at speed can also spread misinformation. The National Weather Service and broadcast meteorologists have put considerable effort into establishing authoritative, trusted presences on social media platforms for exactly this reason. Storm chasers play a more complicated role in this ecosystem than they are often given credit for in popular coverage of severe weather events. The public image of storm chasers, shaped partly by Hollywood and partly by the dramatic video they produce, tends to emphasize the thrill-seeking dimension of the activity, and there is, without question, a thrill-seeking dimension for some practitioners. But the operational reality is that trained storm chasers provide a ground truth function that the automated sensor network cannot replicate. When a tornado is on the ground, a chaser positioned with a clear line of sight to the storm can report that fact in real time to the National Weather Service, confirming what radar may be suggesting and providing specific location information that improves the geographic targeting of warnings. When a tornado is wrapped in rain, invisible on video but indicated by radar, a chaser positioned at an appropriate angle can see it, report it, and potentially provide the critical confirmation that allows meteorologists to issue a more confident warning. The SkyWarn program, administered by the National Weather Service, trains volunteers across the country to serve as official weather spotters. SkyWarn volunteers are not casual observers. They receive training in the identification of severe weather signatures, in safe positioning relative to storms, and in reporting protocols that make their observations useful to forecast offices. Tens of thousands of trained SkyWarn spotters are active across the United States, and their reports constitute a valuable layer of the observational network, particularly in areas where radar coverage is limited by terrain or distance from radar sites. Radar coverage across the continental United States, while extensive, is not uniform. The physical reality of radar propagation limits low-level coverage at distance. Radar beams are emitted horizontally from the antenna, but follow a slight upward curve as they travel outward, due to the curvature of the Earth and atmospheric refraction. At a range of 100 miles from a radar site, the lowest elevation scan may be sampling the atmosphere at an altitude of several thousand feet, meaning that a low-level circulation, or a tornado near the surface, might fall below the radar beam's sampling volume entirely. Areas at the margins of radar coverage, in valleys shielded by terrain, or in the gaps between radar sites, are more dependent on ground-based spotters for low-level storm information. The placement of radar sites in the national network was designed to maximize coverage across populated areas, but the network was not designed with the current level of operational demand in mind. Proposals to fill gaps in coverage through the deployment of supplemental radar systems, including smaller gap-filling radars and mobile units, have been discussed within the meteorological community for years. The resources available for infrastructure investment in weather observation systems are always in competition with other priorities, and the long cycles of capital investment in federal scientific infrastructure mean that improvements in the operational radar network happen slowly relative to the pace at which the scientific community understands the need for them. The private sector has begun to deploy commercial weather radar networks, with companies operating networks of smaller, more numerous radar installations that can provide denser coverage in specific areas, particularly around airports and urban centres, with acute need for detailed weather information. The integration of commercial radar data with the operational products used by National Weather Service forecasters is an ongoing area of development, raising questions about data quality, standards, access, and the appropriate role of private enterprise in a system that ultimately serves a public safety function. All of this radar infrastructure, public and private, feeds into forecast offices where meteorologists are making warning decisions in real time during severe weather events. The human element of this process is easy to underestimate when you think about it from the outside, when the mental image of weather forecasting is an algorithm running in a server room somewhere. The reality is that experienced meteorologists exercise substantial professional judgment in warning operations. They are looking at multiple radar products simultaneously, tracking the motion and evolution of multiple storms, weighing the implications of the velocity data and reflectivity data and dual polarization products, monitoring storm reports coming in from spotters and emergency managers, and making decisions about when the evidence crosses the threshold that justifies issuing a warning with a specific geographic footprint. The threshold question is genuinely difficult. Issue too many warnings for storms that don't produce tornadoes, and you contribute to warning fatigue. Issue too few, and you fail to warn people who need the warning. The performance statistics for the National Warning System show that it performs well by historical standards, with substantial improvements in both lead time and geographic accuracy over the past several decades. But the statistics also reflect a reality that every meteorologist in an operational forecast office understands viscerally. The false alarm rate remains significant. A meaningful fraction of tornado warnings are not followed by confirmed tornadoes. This is not a failure of the meteorologist issuing the warnings. It is a reflection of the current state of the science, the atmospheric signatures that indicate tornado potential on radar, the rotating updraft, the strong velocity couplet, the descending wall cloud identified by spotters are necessary but not sufficient conditions for tornado formation. Many supercells with strong mesocyclones do not produce tornadoes, and the factors that distinguish those that do from those that don't are not yet fully understood. The science of tornado genesis, the specific processes by which a rotating updraft concentrates its vorticity into a surface-reaching vortex, remains an active and difficult research problem. Progress is being made. Research programs that have deployed mobile radar units and instrumented vehicles into the tornado-favorable regions of supercells, collecting data from the near-storm environment with unprecedented density and resolution, have begun to reveal patterns in how tornado formation unfolds. The role of the cold pool, the dome of cooled air that spreads beneath a thunderstorm as precipitation evaporates into it, appears to be critically important. The interaction between the cold pool's boundary and the storm's updraft, the specific geometry and thermodynamic characteristics of that interaction, seems to influence whether a mesocyclone extends to the surface and intensifies into a tornado, or decays before reaching the ground. Understanding cold pool dynamics well enough to use them predictively, to look at the available observations and say with meaningful confidence whether this supercell will or won't produce a tornado, is the kind of capability that would represent a qualitative leap in warning science. It would reduce false alarm rates without sacrificing lead time. It would allow forecasters to concentrate public attention on the most serious threats within a broader severe weather outbreak. It is not yet available as an operational tool, but it is not unimaginably distant either. The research is producing results. The economic dimensions of severe weather, the costs of damage and the costs of preparation, and the costs of warning and response are an important lens through which to understand the investment society makes in meteorological science. The total economic losses attributable to tornadoes in the United States in a significant outbreak year can reach into the billions of dollars. Property destruction, business interruption, infrastructure damage, the costs of emergency response and recovery. These numbers are large enough to attract serious attention from insurance and reinsurance industries, from federal disaster assistance programs, from state and local governments trying to understand their risk exposure. The cost-benefit case for investment in weather prediction and warning infrastructure is, by the analysis of economists who have examined it, extremely favourable. The value of improved warning-led time, measured in reduced casualties and reduced economic losses when people and businesses have more time to take protective action, substantially exceeds the cost of the research and infrastructure investment that produces the improvement. This is a case where the economic argument and the humanitarian argument point in the same direction, which is not always how it works in public policy. Insurance companies model tornado risk at high resolution, mapping the probability of tornado strikes of various intensities across the landscape and pricing coverage accordingly. These models draw on historical records and on the growing body of research about how tornado climatology is distributed in space and time. They also have to grapple with the possibility that historical patterns may not perfectly predict future patterns, given that the atmospheric conditions that support tornado development are embedded in a climate system that is changing. The climate dimension of tornado science is one where careful scientific language is important, because the public communication of uncertainty in this area has sometimes produced more confusion than clarity. Here is what the science currently supports saying with reasonable confidence. The moisture content of the lower atmosphere over the southern plains has increased in recent decades, as higher sea surface temperatures in the Gulf of Mexico drive higher evaporation rates and more water vapor into the flows that supply severe weather systems with their fuel. Higher moisture content, all else equal, increases the potential instability of the atmosphere and the energy available to convective storms. Here is where it gets more complicated. The thermodynamic parameters that govern severe storm development, wind shear in particular, the change in wind speed and direction with height that gives supercells their rotation, are also sensitive to climate forcing, and the projected changes there are more complex and in some respects potentially offsetting. The jet stream, which is a major driver of wind shear patterns across the continent, has been observed to shift in ways that may be connected to Arctic warming, and those shifts could influence where and when the optimal combination of ingredients for violent tornado development tends to occur. What the research suggests is not a simple story of more tornadoes or fewer tornadoes in a warming climate. It is a story of shifted patterns. Tornado activity may increase in some regions and seasons while decreasing in others. The zone of highest risk may migrate. The frequency of outbreak days, the atmospheric pattern types most associated with large numbers of tornadoes occurring in a single event, may change in ways that are still being characterized. None of this is cause for either complacency or alarmism. It is cause for continued research and for planning systems that are adaptive rather than static. End of part 1 of 4. The communities in Tornado Alley and beyond that have lived with tornado risk for generations, have developed their own forms of adaptation that go beyond the formal warning system. Building codes in many of these communities have evolved to incorporate better guidance on the construction of tornado-resistant structures. The question of what constitutes appropriate construction for tornado-prone areas is not simple, because the economics of building construction create real constraints on how much additional protection is feasible in residential and commercial structures. A home built to withstand EF5 tornado winds in excess of 200 miles per hour, would be an extremely expensive structure, likely built of reinforced concrete and steel in ways that bear little resemblance to the wood frame construction that dominates American residential housing. For the vast majority of homeowners in the southern plains, building to that standard is not financially realistic. What is realistic is improving the performance of the most vulnerable structural elements, better connections between the roof framing and the wall framing, better connections between the wall framing and the foundation, attention to the garage door, which is often the weakest element in the exterior envelope of a residential structure and the one most likely to fail first in high winds. Safe rooms and community tornado shelters represent a different approach to the problem. Rather than trying to make every structure capable of withstanding the worst winds, the safe room strategy accepts that ordinary construction may fail in extreme conditions and instead provides a dedicated hardened space, typically a reinforced concrete or steel structure anchored to the foundation, designed specifically to protect occupants during a tornado. Safe rooms meeting Federal Emergency Management Agency standards have been tested to withstand winds of 250 miles per hour, applied to all surfaces simultaneously. A far more severe test than any natural tornado has been conclusively documented to impose. The federal government has funded the installation of residential safe rooms and community tornado shelters through grant programs that help offset the cost for individual homeowners and local governments. The take-up of these programs in high-risk areas has been meaningful but not universal. Cost remains a barrier for many homeowners, and the perception of personal risk is not always calibrated to the statistical reality. People in tornado-prone areas who have never experienced a tornado strike at close range tend to underestimate their personal risk in ways that parallel documented patterns in how people think about other low-probability, high-consequence events. Mobile homes and manufactured housing represent a particular vulnerability in tornado-struck communities. Manufactured housing, even when properly installed and secured, is significantly more vulnerable to tornado damage than site-built residential construction. The structural characteristics of the standard manufactured home, designed for cost-effective mass production and transportation, do not include the same level of resistance to lateral wind loads as stick frame or masonry construction on a permanent foundation. EF1 and EF2 tornado winds that might cause repairable damage to a well-constructed site-built home can destroy a manufactured home. The disproportionate representation of manufactured housing in tornado fatality statistics is a well-documented pattern in post-event analyses. It is also a pattern with an economic justice dimension that does not always receive the attention it deserves in policy discussions. Manufactured housing is often the most affordable option available for lower-income families in rural areas. The people living in manufactured homes are not there because they don't understand the risk. They are often there because the alternative is unaffordable. Addressing this vulnerability requires not just building code or site placement requirements, but broader attention to affordable housing availability and the economics of rural housing markets. Community warning infrastructure, including the siren networks that provide outdoor warning for people who are not connected to electronic media, has also evolved. Modern sirens are electronically controlled and can be activated remotely, individually or in groups, by emergency management personnel responding to a developing threat. The networks are tested regularly, creating the normalization effect I mentioned earlier, but the testing itself has value in ensuring that residents know what the sirens sound like and can distinguish a test from an actual warning event. Some communities have moved toward differentiated signal patterns, distinct siren tones for different threat types, as a way of adding information content to the signal beyond the simple presence or absence of a siren. The National Weather Service's network of weather forecast offices, the local offices responsible for issuing warnings and forecasts for specific geographic areas, has gone through significant changes over the decades in how those offices are structured and resourced. Consolidations that occurred in the 1990s reduced the total number of forecast offices, but increased the geographic area each office covers, with the expectation that better technology would allow fewer forecasters to cover more territory effectively. The technology has indeed improved, but the operational tempo during significant severe weather events can still be intense, with the same small team of forecasters simultaneously monitoring multiple severe storms, issuing and updating warnings, ingesting ground reports, and coordinating with emergency management partners. The forecasters at National Weather Service offices are some of the most skilled operational meteorologists in the world. Their work is not glamorous in the public eye. They don't have the visibility of broadcast meteorologists who appear on television screens during evening newscasts, but they are the people making the real-time decisions that determine when warnings go out and what those warnings say. Their professionalism and the systems and training programs that support it are a genuine public good. The partnership between the National Weather Service and the broadcast meteorology community is an important feature of the American weather information ecosystem. Local television meteorologists serve as translators and amplifiers, taking the official forecast products from the National Weather Service and communicating them to local audiences in accessible, contextualized ways. The good ones know their local area intimately. They know which specific communities in their broadcast area are in the highest risk corridors, which topographic features influence local storm behavior, which demographics in their audience are hardest to reach through standard channels. That local knowledge has real value during severe weather events. The tension that sometimes exists between broadcast meteorologists and the National Weather Service over things like the timing and geographic extent of official warnings and how local broadcasters communicate departure from official forecasts is generally productive in the sense that it creates a system with multiple informed voices offering their best assessments of the threat rather than a single authoritative voice that might be wrong. Redundancy in the warning system has value. Multiple people saying slightly different things about a complicated developing situation is often more informative to the public than a single unified message. The development of social media as a weather communication channel introduced new actors into this ecosystem with highly variable levels of expertise and highly variable standards of accuracy. On the positive side, social media enables the rapid dissemination of storm photos, damage reports and warning reminders from trusted voices to large audiences. Broadcast meteorologists, National Weather Service officers, trained storm chasers with large followings, and severe weather enthusiasts who do careful work all contribute to a social media weather information environment that, at its best, delivers actionable information to people who need it quickly. On the negative side, social media has no effective gatekeeping against misinformation during weather events. Rumours travel fast. Premature damage reports get amplified before they can be verified. Unofficial speculation about tornado tracks and intensities circulates alongside official warnings in ways that can confuse and disorient. And the algorithmic structure of social media platforms rewards engagement over accuracy, meaning that dramatic content, even inaccurate dramatic content, can achieve wider distribution than sober official information. Research into the effects of social media weather communication on public protective action is still developing, but early findings suggest a mixed picture. Social media exposure to weather information increases general awareness of severe weather events, but does not reliably translate into improved protective behaviour. The distinction between being aware that severe weather is occurring somewhere and taking specific action to protect yourself in a specific threat scenario is meaningful, and social media is better at producing the former than the latter. The design of effective risk communication is ultimately a psychological challenge as much as a technological or meteorological one. Understanding how people construct mental models of risk, how they weigh the costs and benefits of protective action, how they process uncertain information in time-pressured situations, is fundamental to designing warning systems that produce the behavioral outcomes we want. The research base here is substantial, drawing on several decades of work in the psychology of risk perception and decision-making under uncertainty, and it has produced a set of principles that inform how warning messages are now designed. Concreteness helps. Abstract threat descriptions produce less action than specific ones. Saying a tornado is expected to impact a specific neighbourhood at a specific time is more compelling to a person in that neighbourhood than saying conditions are favourable for tornado development across a broad region. This seems obvious in retrospect, but the translation of this principle into operational warning practice required deliberate effort and institutional change. Social cues matter. People are influenced by what they believe other people around them are doing. During a severe weather threat, if someone sees their neighbours taking shelter, they are more likely to do so themselves. This is why community-level engagement, in the form of neighbourhood emergency preparedness programs that build social norms around taking warning seriously, can complement the technological warning infrastructure with behavioural infrastructure. Trusted sources matter enormously. People who trust the source of a warning are more likely to act on it than people who don't, regardless of the message content. This is why the credibility of the National Weather Service, built over decades of accurate forecasting and transparent communication, is a public asset that has real safety value. It is also why efforts to politicize or undermine trust in federal scientific agencies have consequences that extend beyond the specific policy debates being contested and into the operational reliability of systems that protect lives. The question of how to maintain public trust in weather warning systems while honestly communicating the inherent uncertainty in those systems is one that occupies meteorologists and communication researchers. Uncertainty is real. Tornado warnings carry genuine uncertainty about whether a tornado will form, where exactly it will track, and how intense it will be. Communicating that uncertainty honestly, without either overstating confidence or creating so much ambiguity that people don't know what to do, requires careful language and a consistent approach over time that builds the public's calibration of what different levels of warning language mean. The National Weather Service's language standards for severe weather products have been updated repeatedly over the years to improve clarity and action orientation. The introduction of more vivid language describing potential impacts, replacing abstract descriptors of wind speed with descriptions of what those wind speeds would do to structures and trees and vehicles, represents an attempt to make warnings more emotionally legible, to connect the meteorological information to the experiential reality it represents in a way that motivates action. In the aftermath of significant tornado events, the meteorological community conducts after-action reviews that examine every dimension of the warning process. Was the tornado warned before it touched down? How much lead time was there? How accurately did the warning polygon capture the actual tornado track? Were warnings updated appropriately as the situation evolved? What can be learned from the storm's characteristics that might improve future warning operations? These reviews are institutionalized in the culture of operational meteorology and represent the mechanism by which lessons from individual events accumulate into system-wide improvements over time. End of Part 2 of 4. The damage surveys that follow significant tornado events are conducted with increasing rigor and produce increasingly detailed records that serve both the immediate purpose of documenting the event and the longer-term purpose of building the scientific knowledge base. A high-quality damage survey today includes not just the rating of structures and vegetation along the tornado's path, but detailed GPS mapping of the damage swathe boundaries, photographic documentation at consistent scales, and classification of every accessible damage indicator using standardized criteria. The data from these surveys goes into archives accessible to researchers across the country and around the world. One of the important scientific products of accumulated damage survey data is the characterization of tornado climatology at fine geographic scales. When you have decades of damage path data, including the geographic coordinates of where tornadoes touched down, where they lifted, and how wide they were at various points along their paths, you can begin to identify patterns in where the most violent tornado events tend to occur. Local topography, proximity to water bodies, soil moisture conditions, all of these factors influence storm behavior at scales below what synoptic weather analysis captures, and the accumulated damage record begins to reveal them. This kind of detailed climatological analysis has practical applications in land use planning and emergency management. A community that understands, based on the historical record, that a particular geographic corridor in its area is disproportionately affected when violent tornadoes strike the region, has information that can inform decisions about where to site schools and hospitals, where to require storm shelters in new residential developments, where to focus public investment in hardening infrastructure. The data exists to support this kind of analysis in many areas. Whether local governments have the capacity and the political will to use it is a different question. The relationship between tornado-prone areas and land use change over time is one of the understudied dimensions of tornado risk management. Development patterns across the southern plains and surrounding regions have changed substantially over the past several decades. Areas that were primarily agricultural or lightly developed when the historical tornado record was being built are now more densely populated. The same tornado path that 50 years ago might have crossed empty ranch land now crosses subdivisions. This is not a uniform pattern, and in some rural areas the opposite is true as depopulation has reduced the exposure of people and structures in certain corridors. But the overall trend of development pressure in tornado-prone areas is toward more exposure, not less, which means that equal or even declining tornado frequency could still produce increasing economic losses. The interaction between tornado risk and the specific geography of how development has occurred also shapes where casualties are concentrated. The distribution of manufactured housing, as I noted earlier, is one dimension of this. The distribution of population by age and mobility is another. Elderly and disabled individuals, people who cannot quickly move to shelter on their own, face elevated risk during tornado events and require specific attention in community emergency planning. School dismissal timing, as one specific example, has been the subject of careful analysis after events where tornadoes struck during or near school hours. Getting children into hardened interior spaces versus releasing them to travel by bus or be picked up by parents during an active severe weather threat involves real trade-offs that emergency managers and school administrators navigate in real time. The built environment of modern communities presents tornado risk in ways that earlier generations didn't experience. Multi-story office buildings, big box retail stores, large warehouse-style structures, all of these have different vulnerability profiles than the residential construction that has historically been the focus of tornado damage analysis. The performance of large-span commercial structures in tornadoes has received increasing attention from structural engineers and the research community, particularly after events where these structures failed during business hours with significant numbers of people inside. The 2013 tornado outbreak in the Oklahoma City area, which included the Moore tornado on May 20th, produced damage to commercial and institutional structures that informed subsequent building code discussions in that region and nationally. The Hawley tornado, moving as it did across an area with lower structural density than a major urban area, primarily encountered the residential and agricultural structures characteristic of rural West Texas: homes on slabs, outbuildings of metal framing and sheeting, agricultural equipment in the open, wooden fence lines, oil field infrastructure. Each of these structure types responds to tornado wind loading in characteristic ways, and the damage survey teams who walked the path of the Hawley storm were reading a landscape composed of these elements, each contributing its evidence to the overall picture of the storm's intensity. The oil field infrastructure that exists across much of west central Texas is a particularly interesting element of the regional damage picture. Pump jacks, wellhead equipment, pipeline infrastructure, associated worker facilities, all of this represents substantial fixed investments scattered across the landscape in ways that create their own category of tornado damage and risk. Oil field facilities are not generally built to residential construction standards. They are functional structures optimized for their operational purpose, and their performance in high winds varies considerably depending on design and installation. A tornado that crosses an active oil field can produce damage with environmental dimensions beyond the structural, creating spill risk from damaged tank batteries and fire risk from compromised equipment. Emergency management for oil field-related tornado damage requires coordination between standard emergency management agencies and the energy industry's own response apparatus. The Texas Railroad Commission, the state agency responsible for regulating the oil and gas industry, plays a role in post-event assessment of energy infrastructure damage in Texas, adding a dimension to the response picture that is specific to this part of the country and its economic character. Agriculture is the other dominant economic activity across the West Texas landscape, and tornado damage to agricultural operations carries its own dimensions. A tornado that destroys farm equipment, granaries, livestock facilities, and irrigation infrastructure creates economic losses that may take multiple growing seasons to recover from, even with insurance coverage. Livestock scatter, cattle that survive but cannot be located for days, is a practical problem specific to rural tornado events that urban emergency management frameworks are not designed to address. County extension agents and agricultural emergency planners have developed specialized protocols for agricultural disaster response that operate alongside but distinct from the standard emergency management framework. The human geography of rural West Texas also presents specific challenges for post-tornado response. The distances involved in providing emergency services across a sparsely populated area where a tornado has struck mean that mutual aid from neighboring jurisdictions is not just helpful, but essential. A county with a small population base and correspondingly small emergency response infrastructure cannot field the resources needed to respond to a major tornado event from its own assets. The mutual aid frameworks that enable counties and cities to share resources during disasters are a critical element of the regional response capacity, and their activation during the May 2nd aftermath in Jones County and surrounding areas illustrated both the value of pre-established mutual aid agreements and the logistical challenges of coordinating large numbers of arriving resources. Recovery from a tornado at the scale of what struck Hawley is a marathon, not a sprint. The immediate emergency phase, search and rescue, medical care for injuries, shelter for displaced people, runs for the first 24 to 72 hours. The relief phase, covering essential needs including food, water, temporary shelter, and emergency financial assistance, may run for weeks. The recovery phase, including the rebuilding of damaged structures, the restoration of utilities and infrastructure, and the longer-term work of economic and psychological recovery for affected individuals and families, extends for months to years. The Federal Emergency Management Agency's disaster declaration process, which determines the availability of federal recovery assistance for affected communities, involves an assessment of the scope and severity of damage relative to a state and local government's capacity to respond. A tornado that causes severe damage in a community with limited financial resources, which includes many rural Texas communities, is more likely to qualify for a major disaster declaration, with its attendant federal assistance programs, than the same physical damage in a more affluent area with greater capacity for self-help. This is intended design, but the process of applying for and qualifying for federal disaster assistance is not straightforward, and many individuals who are eligible for assistance do not successfully navigate the application process. Community organisations, including the non-profit and faith-based sector, fill gaps that formal assistance programs leave open. The American Red Cross provides immediate shelter and feeding support. Volunteer organisations affiliated with FEMA's National Voluntary Organisations active in disaster network coordinate longer-term recovery assistance, including case management for households with complex recovery needs. Community foundations and philanthropic donors often direct resources toward affected communities in the days following a major disaster, supporting local non-profits that have established relationships and operational capacity in the affected area. This informal recovery ecosystem is a genuine resource, though its distribution and capacity vary considerably across the country, with communities that have strong civic infrastructure receiving more robust, philanthropic and voluntary support than those that don't. The psychological dimensions of tornado recovery have received increasing research attention in recent years, driven in part by the accumulating evidence that the mental health impacts of disaster are as significant and as long-lasting as the physical and economic impacts, and often less well addressed. Post-traumatic stress responses in survivors of violent tornado events are documented and clinically significant. Children who experience tornado events, particularly events that involve loss of home or death of community members, show elevated rates of anxiety and post-traumatic symptoms that can persist for years without appropriate intervention. Adults in affected communities show elevated rates of depression, substance use, and complicated grief responses. The challenge of providing mental health support in the aftermath of a rural tornado event is substantial. Rural areas typically have limited mental health infrastructure even in normal times. The workforce of licensed mental health providers per capita in rural counties is far below the ratio in urban areas. When a disaster occurs and the need for mental health support spikes, the community's capacity to meet that need is often overwhelmed. Teletherapy has emerged as a potentially important tool for extending mental health services to disaster-affected rural communities, but its effectiveness depends on having adequate telecommunications infrastructure, which is not always available in affected areas, and on the willingness of affected people to access services through a medium that many find less comfortable than in-person interaction. The resilience literature in disaster psychology, the body of research on what factors help individuals and communities recover effectively from traumatic events, points towards social connectedness as one of the most robust predictors of positive outcomes. People with strong social networks, people embedded in communities with high levels of trust and mutual support, recover more quickly and more completely than those who are isolated. This finding has implications for how we think about disaster preparedness that go beyond the conventional focus on material preparations, emergency supplies, safe room construction, evacuation planning. Investing in social cohesion, in the kinds of neighbourhood and community relationships that sustain people through difficult times, is a form of disaster preparedness with real returns. The small communities of West Texas, including Hawley, tend to score relatively well on measures of social connectedness. The cultural emphasis on neighborly self-reliance that has characterized rural Texas communities for generations translates, in disaster contexts, into neighbors showing up for each other with practical help without being asked. It translates into local churches and civic organizations activating their networks to coordinate care for the most vulnerable community members. It translates into a pace and character of community recovery that may look slower by some metrics, but that often involves a degree of genuine mutual aid that more anonymous urban communities find harder to mobilize. This is not to romanticize rural disaster experience or to suggest that small communities don't face severe challenges in recovery from major tornado events. They do. The financial and institutional resources available for recovery in small rural communities are substantially less than in larger urban areas, and the path to full recovery is genuinely harder in many respects. But the social capital that these communities carry is real, and it matters for outcomes in ways that external observers sometimes miss, because social capital is harder to quantify than insurance coverage or building code compliance. End of part 3 of 4. The physical reconstruction of what the Hawley tornado destroyed will unfold over the months following May 2nd, in ways that will be shaped by the economic circumstances of the affected property owners, the availability of contractors and materials in a regional construction market that may be strained by the broader outbreak's damage across multiple communities, and the insurance settlements that determine how much financial resource each affected household has to work with. Structural engineers and building officials will be involved in the permitting and inspection of new construction, applying the current applicable building codes and, in some cases, voluntary provisions that exceed the minimum code requirements for homes in tornado-prone areas. The question of what minimum standard of construction should apply in tornado-prone areas is genuinely contested. Building codes in the United States are developed and adopted at the state and local level, drawing on model codes produced by national standards organizations that are updated periodically to incorporate new research and engineering data. Texas building codes have been the subject of significant policy debate following major tornado events in the state, with advocates for more stringent requirements arguing that the increased cost of building to a higher standard is justified by the improved probability of survival in violent tornado events, and opponents arguing that the cost increase would price housing out of reach for many families and that perfect should not be the enemy of good. A home built to current standard construction practices in Texas, with proper connections between framing members and foundation, adequate hurricane straps at the roof wall connection, and a structurally sound interior room suitable for use as a shelter during a tornado, provides meaningful protection up through the EF2 range and survivable refuge in a well-designed shelter space even at EF3 intensity. This is not nothing. The vast majority of tornadoes are EF2 or weaker, and a home that performs adequately in that range provides real protection for the real statistical risk that most homeowners face. The argument for requiring more, for EF3 or EF4 survivability at the whole structure level is strongest in the areas of highest historical intense tornado frequency, where the statistical argument for investment in better construction is most compelling. The National Institute of Standards and Technology has conducted detailed technical investigations of tornado damage to buildings following several major events, producing reports that identify specific construction failures and their probable wind speed causes. These reports are used by the engineering and building standards communities to inform code development discussions, and by the design community to identify construction practices worth avoiding. The NIST report on the Joplin tornado, for example, documented specific failure modes in wood frame residential construction that contributed to fatalities and identified design improvements that could reduce vulnerability without requiring the complete transition to reinforced concrete construction that would be economically prohibitive. The progression from research findings to building code adoption to actual construction practice is long and uneven. A research finding published in an engineering journal may take a decade or more to work its way through the code development process and into the additions of the model building codes adopted by state and local jurisdictions. Those jurisdictions then adopt code additions on their own schedules, meaning that construction in different communities may be governed by code additions that are years or even decades apart in their technical currency. And construction to code is not the same as construction that exceeds code, even when exceeding code would be cost-effective in terms of long-term risk reduction. This is not an indictment of the system exactly. Building codes represent a negotiated balance between safety objectives and economic constraints, and the process of updating them is deliberately slow to ensure that changes are based on solid evidence and that the construction industry has adequate time to adapt. But it does mean that the gap between what the science suggests is possible and what the standard system has implemented, and then between what the standard system has implemented and what is actually being built, is significant and persistent. The insurance industry, through the pricing of coverage and the requirements attached to its availability, has emerged as a potentially important mechanism for accelerating the adoption of better construction practices. Insurers who offer meaningful premium discounts for homes with documented above-code construction features, including installed safe rooms, reinforced roof-to-wall connections and impact-resistant roofing materials, create a direct financial incentive for homeowners to invest in resilience improvements. The Insurance Institute for Business and Home Safety has worked to develop and promote the Fortified Standard, a set of construction guidelines developed specifically to address wind hazard vulnerability, as a mechanism for recognizing and rewarding improved construction practices in insurance markets. The uptake of voluntary resilience construction standards has been most robust in coastal areas facing hurricane risk, where the frequency and magnitude of major wind events creates a financial case that is immediately legible to homeowners and insurers. In tornado-prone areas of the interior plains, where the annual probability of a tornado strike at any specific location is lower, even though the consequences of a strike are severe, the financial case for above-code construction is less immediate but still real when modelled over the full life of a structure. Communicating that longer horizon risk argument to homeowners who are making near-term construction budget decisions is a persistent challenge. The broader question of climate resilience in the built environment is one that policymakers, planners, engineers, and community leaders across the country are wrestling with, as the implications of a changing climate for the frequency and severity of natural hazards become more apparent. Tornadoes are one hazard type among many, and the investments required to improve resilience to tornadoes exist alongside and sometimes in competition with investments required for flood resilience, heat resilience, wildfire resilience, and the other dimensions of a changing risk landscape. Setting priorities in this environment requires a clarity about what the most consequential risks are in specific places, a clarity that the growing field of community risk assessment is working to provide. In Texas specifically, the combination of tornado risk across the western and central parts of the state, with hurricane risk along the coast, severe heat risk across virtually all of it, and inland flood risk that has been demonstrating its potential in recent years, creates a complex resilience challenge that no single infrastructure investment or policy intervention addresses comprehensively. The state has invested in emergency management capacity and warning infrastructure. It has faced criticism for the performance of its electric grid during extreme cold events that exposed vulnerabilities in a different dimension of the resilience picture. The management of interconnected risks in a large, economically complex state is genuinely hard work, and the May 2nd outbreak in west central Texas is one data point in a much larger ongoing accounting. Back on the ground in Jones County, the immediate practical reality of recovery from the Hawley tornado is the work of clearing debris, assessing structures, filing insurance claims, making decisions about rebuilding on the same site versus relocating, and navigating the bureaucratic processes that determine what assistance is available and how to access it. These are not abstract policy questions. They are the concrete daily experience of families and property owners trying to put their lives back together after an event that arrived with immense violence and departed in minutes, leaving behind problems that will take years to fully resolve. The people who live in Hawley and the surrounding communities of Jones County did not choose to live in one of the most tornado-active parts of the United States in some casual or uninformed way. They are there because that is where their families have been for generations, because the land supported the agricultural and ranching economy that built the community, because the particular character of the West Texas landscape, its enormous sky and its demanding climate and its deep-rooted culture, is home in ways that are not easily replicated elsewhere. Disaster experiences alter that relationship with place, but rarely sever it. The historical record of tornado events in the southern plains is filled with communities that were struck severely, lost structures, and sometimes lives, and rebuilt. Not always identically, not always in the same economic configuration. But the communities persisted. Hawley will persist. The severity of the May 2nd tornado is not in dispute, and the work of recovery will be substantial. But the community has the thing that research consistently identifies as the most important predictor of successful disaster recovery, which is the social infrastructure, the relationships, the shared identity, the mutual commitment that is harder to build than any shelter, but more durable in the end. The meteorologists who will continue to study the May 2nd outbreak will use it to refine their understanding of the atmospheric conditions that produced it, to examine what the storm's radar signatures can tell them about the predictability of its intensity, and to look for patterns that might allow future events of this kind to be anticipated with greater specificity. Every major tornado event is a natural experiment that adds to the archive of knowledge, filling in the map of what the atmosphere can do and why. The storm chasers who documented the Hawley tornado will study their footage and their data for the same reasons, contributing their ground-based observations to the scientific record and sharing what they captured with the wider community of people who are drawn to understand the most powerful convective events the atmosphere produces. Some of them will teach, passing on what they've learned about safe and responsible storm observation to the next generation of researchers and chasers. Some will continue doing the work directly for as long as they can, driven by the combination of scientific curiosity and something harder to name, something that is really just the human response to witnessing the atmosphere at its most extreme. The desire to understand something immensely powerful, to be close to it and study it, and ultimately know it better than you did before. The National Weather Service forecasters who issued warnings on May 2nd will conduct their after-action review, documenting what worked well and what could be improved, adding their findings to the institutional memory that accumulates across decades of operational forecasting. Their work is continuous and largely invisible to the people it protects. The warning that reaches someone's phone and sends them to the bathroom floor with their arms over their head. The warning that turns out to be right, that comes 18 minutes before the tornado touches down nearby. That 18 minutes is the product of enormous collective investment in science, technology, operations, and the training of skilled human beings who can read what the atmosphere is telling them in real time. That investment is worth defending and worth continuing to make. The sky over west central Texas will again, on some future afternoon when the dry line sets up and the atmosphere is primed, turn that particular shade of green that people on the southern plains recognize immediately. Another supercell will organize, another mesocyclone will deepen, another wall cloud will descend. The question for that future storm will be the same questions that have always defined this relationship between human beings and the most violent weather on Earth. How much warning is there? How accurately does the warning communicate the threat? Do the people in the path take action? The answers to those questions are not fixed. They are the product of choices about investment in research and infrastructure, choices about how communities are built and where, choices about how risk information is communicated and received, choices about the culture of preparedness that communities build and maintain. Every improvement in warning technology, every advance in the science of tornado genesis, every building code update, every safe room installed, every skywarn spotter trained, every emergency manager who walks a damage path and carries that knowledge back to the planning table, every one of those is a choice that shapes the answers. The tornado that struck Hawley on the afternoon of May 2nd was an EF3, a high-end one, violent by any measure. It swept a concrete slab clean. It carved a path across the landscape that will remain visible for a long time in the damage patterns of trees and structures and disturbed soil. It is part of the record now, part of the archive of what the atmosphere of west central Texas has done across the history of people living beneath it. The storms accumulate in the record. The knowledge accumulates too. And in the accumulation of knowledge, in the slow and incremental and sometimes frustrating but ultimately real progress toward better prediction, and better warning and better protection, is the only honest answer to what the atmosphere gives us to work with. The sky is vast here. The horizon goes forever. And on the right kind of afternoon in May, when the green settles in and the air goes still, the question of whether you are ready for what comes next is not abstract. It is immediate and personal, and it belongs to every person standing beneath that sky.